wanted to work through the worksheet on Kirchoffs rules and solving a complex circuit with Kirchoffs rules. The circuit is shown here. It contains 3 arms. In each arm is a battery, an EMF, and they're labeled epsilon 1, epsilon 2, epsilon 3. We know the EMFs, 70, 60, and 80 volts. In each arm is also a resistor. They're labeled R1, R2, R3. We know their values. They're 2 kilo ohms, they're 3 kilo ohms, and 4 kilo ohms, respectively. And this worksheet asks us to figure out the 3 currents that flow through the 3 arms and also figure out the voltages across the 3 resistors. So we're going to solve all this with Kirchhoff's current rule, Kirchhoff's voltage rule. To get things going, I've indicated on the circuit the 3 currents that I'm going to work with. Now, I've indicated I1 on the left-hand arm, I2 on the center arm, and I3 on the right-hand arm. I've just guessed the directions of them. So I guess that I1 and I2 were down in the 2 arms that they're flowing in. I3 is up. That's just a guess. And we'll see whether I get that right or get that wrong. It doesn't matter in terms of solving the sizes of the currents in the circuit and hence determining the voltages in the circuits. If you guess right, you just get a plus sign for a current. If you guessed wrong, you'll get a minus sign for a current, and you can then just go back if you like and change the direction of the arrow. I also added on the sketch the 3 sources for 3 equations that will enable me to solve for the 3 unknowns, I1, I2, I3. And those 3 sources are going to be applying the current rule to this node downstairs here and applying the voltage rules to this loop here in this left-hand section of the circuit and this second loop here, which is around the entire circuit. So I picked one of 2 nodes. I could have picked either one of them, and I picked 2 of 3 loops. There's also a loop over here on the right-hand side of the circuit. And I could have made alternate choices for those, but that's what I'm going to work with to make 3 equations with 3 unknowns and then solve for those 3 unknowns. And that's basically the plan. One final comment is that as I solve this problem and as I input the values of the voltages and the resistances and solve for the currents, I'm going to use this set of units. So the voltages are given in volts. I'll put the numbers in volts. The current, the resistances are actually given not in ohms, but in kilo ohms, units of thousands of ohms. And I'm going to use these numbers, kilo ohms, when I put in the resistances of the resistors. If I do that, it means that the currents that I get out won't be in the units of amps, rather they'll be in the units of thousandths of an amp, milliamps. And so my currents will be in these units of milliamps when I finally calculate them. You can see that this scheme of units will work if you think about Ohm's law. Over here is volts, and we're going to be working in the units of volts. Over here on the right is current times resistance. Now, often we work in amps times ohms, but I'm going to work in kilo ohms. So this is a 1,000 ohms for the resistance, and that means I'll work in milliamps, 1,000th of an amp. And a milli times a kilo, 1 over 1,000 times 1,000, gives us just unity. And so the units over here will be volts. So this is a consistent set of units of volts for voltage, kilo ohms for resistance, and milliamps for current. So now I'm going to write down my 3 equations for my 3 unknowns. Let me start with the simplest one, which is the one for this junction here, this node here. The current rule says that the current flowing into this node is equal to the current flowing out of this node. I1 and I2 flow in, so that's their sum is the total current flowing in. I3 is flowing out of that node, and so that current in, I1 plus I2, must be equal to that current out, that's I3. For my second equation, I'm going to go around this smaller loop in the left-hand side of the circuit. Now, you walk around this smaller loop, let's say start over here. I'm going to go up through this battery. I'm going to go down in potential through this battery, and then I'm going to go through resistor R1 and R2 back to where I started. When I go up through this battery, I'm going to increase my potential by 60 volts. Then I'm going to go down through this battery, decrease my potential by 70 volts. The net change in the potential as I go through these two batteries is going to be minus 10 volts. And so I just wrote the minus 10. It really was a plus 60 minus 70. Then I go through the resistor R1. Its resistance is 2 kilo ohms. The voltage across it will be the product of its resistance times the current through it. So that's 2 times I1. And since we're walking in the direction of the current, then that's a negative sign. We're walking down the potential hill as indicated by the direction of this current. So that's the minus 2 I1. Then similarly, the 3I2, the plus 3I2, I'm walking through this resistor R2. It's 3 ohms, so the voltage change is 3 ohms times kilo ohms times the current, I2. And this time I'm walking opposite the direction of the current, so this would be up the potential hill. So this is 3I2 is the change in potential through that resistor. The sum of these changes in potential, according to Kirchoffs' rule, must be 0 because we've now completed the loop. And so this is the second equation that I've generated. Now, I rewrote that equation. We'll see why I did this later on, but I rewrote this equation. If you look at it, it's a relationship between I1 and I2, the currents in the two arms here, the left arm and the center arm. And I'm just going to rewrite it in the form that I2, the current in the center arm, is this function of I1, the current in the left arm. So I just rewrote the equation by moving I2 from one side of the equation to the other side of the equation and dividing by a factor of 3. The last equation I got by walking around the entire circuit, kind of the outer walls of the circuit. So that means I went along the right arm and the left arm, but I didn't go through the center arm. Again, Kirchoffs' rule said add up the voltage changes when you walk around the circuit, and the sum of the voltage changes will add up to 0 because there'll be some ups and some downs. As you walk around this outer wall, notice you're going to go through two batteries, and there'll be two changes in potential associated with epsilon 3 and epsilon 1. You're going to go through two resistors. There'll be two changes in potential associated with R1 and R3. I walked counterclockwise around the circuit. I went up 80 volts when I went through this battery over here on the right. I went down 70 volts when I went through this battery over here on the left. So again, I just combined those. I went up 80, down 70. So that's a net change of 10 volts. So this is the plus 10 here. I'm also going through two resistors. Resistor R1 downstairs here. I'm going in the direction of the current. The change of potential is given by Ohm's law, is the current times the resistance. That's the 2I1. So this is a change in potential. It's a downward change in potential. I'm walking through the 4 ohm resistor, R3 up here. The change in potential is given by Ohm's law again, IR. So that's the 4 kilo ohms times I3. That's the current through R3. This time, I'm again actually walking in the direction of the current flow. So This is also a negative change in potential. I'm going down the potential here. Again, this is the equation I've generated with this Kirchhoffs voltage rule for this particular loop. I'm going to rewrite this equation like I rewrote the previous equation, actually as an equation for I3. The equation is a relationship between I1 and I3, and I'm just going to write it as I3 in terms of I1. Again, the procedure is moving the term with I1 from the left-hand side to the right-hand side of the equation. Then I would be dividing by 2. And if you do that procedure, you get this, this equation here for I3. Well, that's really all the physics work done. We've got 3 equations. I can label them. Let's label these 3 equations. There's this one from the current rule. I'll call that number 1. There's this one from the voltage rule. There's a second one from the voltage rule. And these are 3 equations for 3 unknowns. When I start doing the math part of the problem, I'm going to use this equation here, obviously, this relationship. Then I'm going to work with this equation here and this equation here. So these are my 3 working equations. Specifically, what I'm going to do, I'm first going to use equation number 1, which contains all 3 currents. I'm going to replace I2 in it using equation number 2, which tells me I2 in terms of I1. I'm going to replace I3 in equation number 1 with equation number 3, which tells me I3 in terms of I1. That makes one equation with one unknown. And I'll solve for that one unknown. I'll figure out I1. And so that's what I did in this line here. This equation looks complicated, but it's really I1, current in the left-hand arm, plus I2. This is the current in the center arm. This is I2 in parentheses, equals I3. This is the current in the right-hand arm. It's just that I replaced the current I2 in the center arm with my expression for it in terms of I1. And I replaced current I3 with my expression for it in terms of I1. And so I've made this single equation with a single unknown. And if you collect together the terms involving either the I1s on one side of the equation, you collect together the constant terms on the other side of the equation, you solve for I1. And here's the value that I got by rearranging this equation here. I1 is minus 0.385 milliamps. Well, now you've got I1, you know that current. You can go back to the second and the third equations. And so for I2, by plugging in I1, solve for I3 by plugging in I1 again. And that's all I did here. So these 2 equations, one for I2 and one for I3, are equations 2 and 3. It's just I replaced the current I1 with the now known numerical value. It's minus 0.385 milliamps. And when you do that, you get these values for the currents in the 2 other arms. They're both positive. I1 was negative. Well, at that point, we've solved the circuit for the 3 unknown currents. We found their sizes, I1 and I2 and I3, and we actually also found their directions. We found that because I2 and I3 are positive in our solutions, the directions indicated on the diagram are actually correct. I2 does flow down, I3 does flow up. Because I1 is negative in our solution, that means that actually the current in this left-hand arm wasn't down. That was my guess that it was down. It's actually up. And so I'll just change that here. The last part of this problem says figure out the voltages across the 3 resistors due to these 3 currents and figure out which end of the resistor has a higher polarity, higher potential, which end of the resistor has a lower polarity, a lower potential. That's very easy now. We've got the 3 currents because we can just apply Ohm's law to the 3 resistors and figure out the voltages across the three resistors, because we now know the resistance of the resistors, and we also know the currents flowing through the resistors. So let me just show you for the first resistor, R1, the procedure is exactly the same, identical for the other two resistors, R2, R3. So for the first resistor, the potential across it is given by Ohm's law. So V1 will be equal to I1 R1. The current we found, I'm just going to plug in the size here. I'm going to talk about the direction later. The current size is 0.385 milliamps. The resistance of the resistor is 2 kilo ohms. If we multiply the current in milliamps, the resistance in kilo ohms, we get a voltage in volts, and it comes out to be 0.77 volts. So that's 0.77 volts across this resistor here due to this current flowing through it. Now, we figured out that the current was actually, unlike our guess, going up the left-hand arm. And so currents always flow, conventional currents, direction that positive charges would always flow down the potential hill. So if the current is flowing to the left through this resistor, this must be the positive end, and this must be the negative end. So I also calculated V2 and V3 by the same procedure of Ohm's law. And the values that I got when I multiplied the currents, which are listed here, they're about 3 amps and about 2.7 amps, by the resistances of R2 and R3, which were 3 ohms, 3 kilo ohms and 4 kilo ohms. I got for R2 a potential across R2 that was 9.23 volts, and for resistor R3, a potential across it that was 10.77 volts. And so I've indicated those on my diagram upstairs here. In this case, the currents were flowing in the direction of my initial guesses. And so for resistor R2, the current is flowing down this arm. So upstairs here is the higher potential of the resistor. And downstairs here is the lower potential end of the resistor. And then the reverse is true for the resistor R3. The current is flowing up that arm. And so this end over here on the right-hand side, that's going to be the more positive potential. This end over here on the left-hand side, that's going to be the more negative potential. Anyway, that was an example of a electrical circuit, a complex electrical circuit. Can't be solved with the concept of an equivalent resistance to figure out the currents and voltages in the circuit. We had to use Kirchoffs' rules, current rule, voltage rule, to solve this circuit. We went about using the rules to form 3 equations for the 3 unknown currents in the circuit, I1, I2, I3. That was the physics part of the problem. We were careful to get the senses or the directions of the potentials as we walked around loops in the correct sense, whether they were increases or decreases in potential. That's important. That generated 3 equations for us with the 3 unknowns. Then we had the mathematical problem of solving the 3 equations for the 3 unknowns. Then, once we got the 3 currents, we're home and dry, basically. If we want the potentials across the resistors, you just take the current through each resistor, multiply by the known resistance of each resistor. That will give you the potentials. And we were able to figure out not only the sizes of the potentials, but now knowing the directions of the currents, we were able to figure out the senses, the polarities of the potentials. One thing to note in this problem, as I say, we guessed the current directions to begin with. And if you guess right, then you'll get a positive value for the current. If you guess wrong, you'll get a negative value for the current. But either way, whether you guess right or wrong, the values, the numerical values, the sizes of the currents will be the correct sizes of the currents. It's just you may have to reverse the direction of the current on your diagram. You might have to reverse the polarity of a resistor on your diagram.